Okay, let's talk about section 5.1. In 5.1, 5.2, and 5.3, we will discuss some basic properties about polynomials, rational functions. So now first, let's talk about 5.1, polynomial functions and the models. Okay, so what is a polynomial function? Let's see the definition, which is first clear the definition. A polynomial function is a function of the form f(x) is a sub n x to nth power, a sub n minus 1 x to n minus 1's power, add up to a1 x and a0. Okay, whenever you have a function of such form, it's called a polynomial function. And an minus 1, a1, a0 are real numbers. And n is a non-negative integer. N is a non-negative. Non-negative means it can be 0, a positive or 0. Okay, the domain of a polynomial function because you can let x be whatever real number. So the domain of a polynomial function is the set of all real numbers. It's a set of all real numbers. So that is the definition. Okay. In this part, all the an's are called coefficients. An, a0 are called coefficients. And n is called the degree of f. N is called the degree of f. And here we have a special situation. an minus 1, a1, a0, they are all real numbers. Possibly they are all 0. So if they are all 0, you will get so-called the 0 polynomial. For the 0 polynomial, there is no degree. It has no degree. 0 polynomial is not assigned a degree. No degree. Has no degree. Okay? So when all the coefficients are 0, the corresponding polynomial function is called the 0 polynomial function, and it has no degree. So we can say that if there is a statement that says all the polynomial functions have a degree, it's wrong. The 0 polynomial has no degree. Okay? For example, if we have 2 minus 3x to 4, so it is a polynomial function of degree 4. So when you talk about polynomial function, you just see if it is x to a certain power, x to a certain power, x to a certain power, and you do addition, subtraction. Degree, you just check the highest power, okay? If you have a square root, you see here, you already read it, square root of x. It is not a polynomial function. Okay, and if you have this x squared minus 2 over x cubed minus 1, this is not, sorry, not, my bad, not a polynomial function. Okay, and of course, if we have a 0, it is a polynomial function. With no degree. With degree unassigned, with no degree. The same thing. Okay, so that's the definition. So what is a polynomial function? Polynomial function is a large class of functions. We actually already have a few special examples. So let's see. First, no degree. It corresponds to only 0 function, 0 polynomial, no degree. And the graph is x-axis. Graph. Okay, and if it has degree 0, degree 0 is arbitrary non-zero constant function. Non-zero constant. Non-zero constant. Non-zero constant has a graph horizontal lines with y-intercept k. Horizontal lines with y-intercept k. And then if you have a degree 1 polynomial function, ax plus b, mx plus b, this is a linear function. We call it a linear function. Linear function is just non-vertical lines. Whenever you have linear function, it's non-vertical lines. And if you have degree 2, fx is ax squared plus bx plus c, it's a quadratic polynomial. Quadratic function. For the quadratic function, it's a parabola. The graph is a parabola. It has open up, open down 2 cases, depending on the sign of a. Okay, so that's actually the special case of polynomial functions. And the polynomial function has some nice property. First, we will the graph. The graph of polynomial function is continuous and smooth. Okay, so here we have two technical words. One is called continuous, one is called smooth. Okay, so we cannot define continuous and smooth concept in mathematics so far, but we just explain the idea. Continuous. This word means that the graph has no gaps or holes. Okay, so we see what graph is not continuous. We exclude that case, we will understand what continuous means. Gaps, this is a gap. Like a jump or gap, this is a gap. Holes, this is a hole. Okay, continuous function means the graph cannot contain such situation. Smooth. Smooth means that the graph has no sharp corner or just corners or cusps. Corner, what is a corner? This is a corner. This is a corner. What is a cusp? Cusp, this thing is called cusp. Corner and cusp are different. Corner, here if you put in the calculus we will see that here if you put the tangent line from the left and the tangent line from the right, they both exist. Cusps, it means from the left side. I mean, this is one type of cusp. You can go to the down, you go point down. From one side, if you compute the tangent line, it's vertical. From right side, it's also vertical, but the rotation direction is different. So this is a cusp. But anyway, we don't want this point. If there's no such point, then it's called smooth. No such point is called smooth. And the graph of polynomial function is continuous and smooth. And in fact, the smooth is stronger than the continuous. Okay? So we're not going to discuss it in detail, but we just mention the graph of a polynomial function is very good. Okay. First, we don't study the general polynomial function. We study the special one, the power function. What is a power function? The power function, a power function of degree n is a monomial function of the form of x equal to ax to n. Ax to n. And here where a is a real number and n is a positive integer. So we do want a function. We don't want a constant function. So that's why we want the degree strictly greater than 0. If it's equal to 0, then it's a constant function. It's not that interesting in the discussion. Okay, so here, if we want a real function, not constant, we require the degree strictly greater than 0. And monomial just means it has one term. You see here, it is just one term from the polynomial function. Okay, this is called a power function. The power function comes from the x to nth power. With it only contains a coefficient. So the power function can have coefficient greater than 1. Let's put here. Then how do you get the graph? The graph means you stretch with the coefficient 3, right? You stretch it, or you get a coefficient less than 1, you compress it. We use word stretch, compress, just depending on the value. And if you have a negative sign, with reflect. Reflect the graph of x squared with respect to the x-axis. So anyway, we can do this either stretch, compress, or reflect process to get the graph of the corresponding power function. So that's an advantage. So we know what it looks like. And now let's get some details. For the details, let's see first power function. We have an integer n. So n has two situations. N is even. If n is even, we know that for the arbitrary x, if it is negative with an even power, it's still positive. It's positive with even power, it's positive. And then what we get negative x to n is equal to x to n. Because n is even, this negative sign is killed by the even power. So this f with a x to n, a is just coefficient, does not change the property. So this is an even function. That's a proof. That's a proof. And actually that's a reason we call it an even function, because it has a similar property as an even power function. So it's an even function. Even function, the graph is symmetric. With respect to the y-axis. If a is positive, it's this way. If a is negative, it's this way. Okay, positive, negative. If we use calculator to draw a precise formula, a precise graph, if we want to make the graph more precise, we will see the following property. I just try to demonstrate. Use the case when a is positive. sorry, not that one. Okay, so when x is 0, when x is 0, y is 0. When x is 1, y is 1. When x is negative 1, remember we're talking about the even case, it's still negative 1, positive 1. So all the ax to nth power, a positive, will pass 0, 0, 1, 1, and negative 1, 1. The graph of, sorry, let's assume a is equal to 1. So all the power function x to nth power will pass through 0, 0, 1, 1, negative 1, 1, those 3 points. And there's small difference, very subtle difference. The difference is the following. So let me draw it and I explain it. This difference can be observed from the better graph, but let's just try to demonstrate. Okay, possibly, let's assume this is x2, not assume, let's assume this is x squared, this is x to 4. The property is that when n is bigger, 4 is greater than 2. When n is bigger, between 0 and 1, the graph is more flat. And after 1, the graph is more, the graph grows faster. Here the same thing because it's symmetric. Okay, so on 0, 1, n is bigger, the graph is more flat. On 1 infinity, n is bigger, the graph increases faster. The graph is more steep. Technically, the graph is more steep. Okay, so that's all the phenomenon you can only observe when you get a better graph, because it's very small region with a just a simple point you may not see it clearly. Okay, so that's an observation. Let's summarize the observation. We see what we have. The observation is the following. First, we're talking about a positive even integer, y equal to x to nth power. We ignore that coefficient. The coefficient can be recovered by the stretch, compress, and reflect. Okay. So first property, f(x) x to n is even. The even function. The graph is symmetric with respect to the y-axis. Okay. And second, the domain. The domain is the set of all real numbers. The range, you see here, the range is always above x-axis, including this 0. Okay, domain range. And 3, those 3 points are the common point. 0, 0, 1, 1, negative 1, 1 are in all x to nth power. The graph always contains those 3 points. And 4, n is bigger or greater, n is bigger the function increases more rapidly in absolute value when x is less than 1 or x is greater than 1. Less than negative 1 or greater than positive 1. So basically just say it's go very fast when it's either on the left side or on the right side. Okay? So, and when x is between negative 1 and positive 1, when it's in the middle part, the graph tends to flatten out and lie closer to the x-axis. Okay. So that's the basic properties for the even power function x to n. Okay, and we always keep this graph in mind. After we studied the property of the even power function, we will study the property of the odd power function. You use a calculator to sketch it. It will be like this. Remember here we assume n is odd. N is odd. Okay, so odd power function. And similarly, this is for general one odd power function. If you have more than one odd power function, you will see something like this. Okay, so you can expect a similar thing. That place in the even case, if it's more flat in the middle, more steep on two sides, the power is bigger. Here is similar thing. Possibly you will have this is y equal to x cubed, this one, and this one is y equal to x to 5. Okay, and you will see that the graph, the function becomes a odd function. The graph is symmetric with respect to the origin. Okay, so and outside it's more steep, inside it's more flat. And in this case, three special common points are 1, 1, 0, 0, and negative 1, negative 1, because negative 1 to odd power is still negative 1. Okay, so we have the similar list of the properties of y equal to x to n greater than 0, odd integer. Odd integer, similar. Okay, 1 fx is x to n is odd. Odd function, odd we mean x negative, f of negative x is negative fx. In this case, it means negative x to nth power is negative x time negative x to nth power. Be careful, we have this condition. We assume this is an odd number. And whenever you have odd function, the graph is symmetric with respect to the origin. Okay, so that's the first one. And The second one, the domain is set of all real numbers. It's defined everywhere. The range is also from negative to positive infinite, so it's from bottom to top. 3, the common points. This time it will get a -1, -1, 0, 0, +1, +1 are in, or fx equal to x2. N odd. Keep in mind n is odd. And 4 is a similar thing. So n is bigger. The function increases in absolute value. Rapidly. When x is less than -1 or x is greater than 1. Here, we actually don't need this absolute value because this is always positive, so this part is not useful. We need absolute value only in this part. And when x is between -1 and the +1, the graph is more flat and closer to the x-axis. Closer to x-axis. Okay, so that's the general property for the x to nth power. N is even and n is odd. No absolute value here. It's always positive. Okay. So here let's see the simple example. Graph fx is equal to 1 minus x to 5. We're going to use a transformation to graph it. So how do we use a transformation to graph it? First, you graph x to 5. It's odd power, so it's like this. And you get a negative sign. Flip it. You just flip it down, up and down. And then +1. It's a negative x to 5 and +1. So you're going to lift it 1 unit up. And that's it. That's it. Okay. Another example. We're going to graph fx equal to 1/2 x minus 1 to 4th power. So first, you have x to 4th power. It's x to 4th power. And then you get x minus 1 to 4th power. X minus 1, you're going to move it to the right. Minus 1, 1 is positive, move to the right. and you're going to compress it with a coefficient 1/2. Like basically you squeeze it vertically. Originally it's 1, now it becomes 1/2. It's more flat. Compression makes the graph more flat. A similar shape but more flat. Okay, that's a process to sketch the graph using transformation. Okay, and next we're going to try to identify the real zeros of a polynomial and the multiplicity. So what is a zero of a real zero and the multiplicity? What is a zero? Okay, so whenever you have a graph, you check the intersection point or the X-intercept, and they mean at those points fx is equal to 0. Okay, then those values are called the zeros of the function. And there are two types of zeros. One, we say this is cross x-axis. This is cross x-axis. Here we say it touch x-axis. Here's cross x-axis. This is a cross, cross, touch, cross. Okay. Okay, so first let's see the definition. If f is a function and r is a real number, for which fr is equal to 0, then r is called a real zero of f. R is called the real zero of f. Okay, so whenever it makes the function equal to 0, it's called the real zero. When we study a little bit, we will have the following equivalent statement about this real zero. Okay, the following are equivalent. Whenever you see this, just means you will see several statement. All the statement, one imply the other. 1, r is a real zero of a polynomial function f. Here, this 0, it can the f can be whatever function. It's not necessarily a polynomial function, but the following are equivalent only for polynomial functions. Okay. 2, r is an x-intercept of the graph of f. 3, x minus r is a factor of f. 4, r is a solution of fx equal to 0. fx equal to 0. Okay, so those 4 statements are equivalent. Whenever you see one of them, it just means you have a 0. So from the third case, whenever you have a 0, x minus it becomes a factor. So for example, find a polynomial function of degree 3 whose zeros are -3, 2, and 5. -3, 2, and 5. Okay. So -3 is a 0. Then x minus -3 is a factor. Two is a 0. X minus 2 is a factor. 5 is a 0. X minus 5 is a factor. Okay, so for each of 0, you will have different factor. Those factors are mutually exclusive. So what we get x minus -3. So x plus 3 times x minus 2 times x minus 5 is also a factor of f. A factor of f. We're looking for the polynomial function f. And this one, if you do multiplication, you already have degree 3. This one already has degree 3. So the polynomial function, our polynomial function fx can be, fx is just x plus 3, x minus 2, and x minus 5. Okay, this is one possibility. It's not unique. You can put whatever coefficient here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever coefficient. They always satisfy the condition. So we just find one. We don't bother to pick up some weird coefficient a. The first leading coefficient. It doesn't matter. If you want to do the multiplication, you do multiply it out. It's x cubed minus 4x squared and minus 11x and plus 30. You see here, it already has a degree 3. And if you want to see the graph, so far you can just use a calculator to check the graph. The graph is like this. So it has zeros, -3, 2, and 5. So the x-intercept, so -3, 2, and 5. And use a calculator, you see that it looks like this. Okay, this graph is from the calculator. Okay, so we will study in detail about this type of stuff. And now let's see. Sometimes, for example, your polynomial, it could be like x minus 1, x minus 2 cubed. There are 3 copies of x minus 2 and x minus 3 fourth power. If the same factor appears several times, this is called a repeated 0. And this power is called multiplicity. Okay, so if x minus r to mth power is a factor of f, and x minus r to m plus 1, if you increase it, is not a factor of f, then r is called a zero of multiplicity m of f. A zero of multiplicity m of f. So we just give it a multiplicity. A multiplicity 2 means it appears 2 times. Multiplicity 10, it means it appears 10 times. If this multiplicity is greater than 1, we say it's repeated. It's a repeated 0. It's a repeated 0. So here we see that this 1, for this example, 1 has multiplicity 1, and 2 is a 0 of multiplicity 3. It's a 0 of multiplicity 3, and this 3 is a 0 of multiplicity 4. Okay, so that's multiplicity. Now let's try to graph the polynomial using the X-intercept, or using the zeros. Assume we have x squared, x minus 2. X squared, x minus 2. First, x, y intercepts. And y-intercept is always f0 when it is well defined. f0, x is 0, 0, y-intercept is 0. X-intercept are the zeros of the polynomial functions. Remember that we have the equivalent statement. Intercept, zeros. Zeros give you the factors. So you check the factor. Here you have x squared. X squared is x minus 0 squared. So the corresponding 0 is 0. This 0 has a multiplicity 2. Here you have 0 and 2. The 0, 2. Okay, so x-intercept are 0 and 2. 0 and 2. And when you have 0 and 2, you will check, you will have, so far here you have 3 intervals. For those 3 intervals, you pick up the sample point. For example, here you select the -1, here you select the 1, here you select the possibly 3. You pick up sample point. You try to evaluate the original function. At -1, you check it, f -1. What is f -1? -1 squared is 1. -1 minus 2 is -3. 1 times -3 is equal to -3. So it's below the x-axis. And when you get 1 here, 1 squared is 1. 1 minus 2 is -1. So it's also below the x-axis. Okay? And when you get 3 here, 3 squared is 9. 3 minus 2 is 1. So f3 is 9. It's positive. So it means it's greater than, so it's above the x-axis. So you use sample point to determine over each interval function f is positive or negative, is above the x-axis or below the x-axis. Okay, so with 0 and 2, there are 3 intervals. There are 3 intervals, and you can just pick up sample point, choosing sample point -1, 1, and 3. Those sample points are from each interval, not in. You cannot select the 0 and 2, so you do have to select some point inside the interval. Choose sample point -1, 1, and 3. We see that from -infinity to 0, and from 0 to 2, fx is negative. Fx is negative. Sorry. Here's negative. Here's negative. So over this interval and over this interval, fx is negative. And from 2 to infinity, fx is positive. Negative means the graph is below x-axis. Positive means the graph is above x-axis. Above the x-axis. So this is a greater than or less than. And next, without additional information, we have to randomly estimate it. So for example, let's you have 0, 1, 2. So when x is -1, f -1 is -3. 1, 2, 3, -3. When x is 1, f1 is -1. Okay, and 1, 2 is x is 3, f3 is 9. It's very high, very high. We cannot touch it. Okay, when you have those points, this above, you're going to sketch the connect them smoothly. We mentioned before, the graph of the polynomial function is smooth, so just try to connect them smoothly. So the graph of the function will be more or less like this. Don't use some crazy curve to connect them. You cannot say, oh, let's do some crazy curve. Don't do that. Even though we have a sketch, but we try to use some smooth, straight curve to sketch. Yeah. Don't make them crazy. Why it's not this, why it's not that way. So far we cannot explain, we just get this. And from here you will see that, remember that we mentioned 0 is a multiplicity, has multiplicity 2. 2 has a multiplicity 1. So from this example, we have some hypothesis or the suggestion or the hint. If R is a 0 of even multiplicity, like this, x squared x minus 2, this is even. If you have an even multiplicity, the graph touches the x-axis. If R is a 0, we're talking about a 0, not arbitrary point. If R is a 0 of an odd multiplicity, like this, the graph crosses the x-axis. So we so far we cannot prove them. We just get the conclusion from this example. Okay, so that's everything we can discuss in this hour. We will continue the discussion next time. We will get some even more clear example, more clear reason why it looks like this or look like that. Okay, we stop here today. Thank you.